Hi everyone, I'm Shamal, and I'm going to be talking about optimal non-adaptive tolerant Junta testing via local estimators, and this is joint work with Shivam Nadampally. Great. So I'll start by defining Juntas. So we're going to be interested in Boolean functions in this talk, and these are functions that are going to take values from the plus minus 1 to the n cubed and output values to plus minus 1. And we say that a Boolean function f is a k-Junta if it only depends on k of its n inputs. So in this example below here, we have x1, xor, x2, and this is a 2 Junta because it only depends on the first two coordinates and doesn't look at the remaining, n minus 2 of them. Now, Juntas form a central concept in the analysis of Boolean functions, for instance, where they're shown to approximate many other functions. Also, they appear in learning theory, where several of the interesting open questions there are about learning Juntas, as well as attribute-efficient learning of various particular concept classes, and in machine learning, where they're motivated by the feature selection problem. So this talk is primarily going to be considering testing Juntas. So what is this problem? So in the standard model, we're given query access to an unknown function f, and we want to design an algorithm that accepts when f is a k-Junta and rejects if every k-Junta disagrees with f on 10% of its inputs. Such test has to be randomized, so we like this distinction to be made successfully 2/3 of the time. And we're going to be interested in how many queries such a tester needs to make. Great. Now there's two flavors of testers. There's non-adaptive testers and adaptive testers. So we say that a tester is non-adaptive if its queries don't depend on the answers to previous queries. So essentially, a non-adaptive tester looks as follows. It asks a bunch of queries. It receives all of their answers at once, and then it sort of puts everything together in order to accept or reject, right? There's no more, yeah. On the other hand, an adaptive tester is allowed to ask queries depending on the answer to previous queries, right? So, what the next question it's going to ask may depend on sort of what it's been told in the past. So clearly adaptive testers are more powerful than non-adaptive testers, but non-adaptive testers are often, simpler and they're highly parallelizable, and so they're oftentimes desirable for this reason. Great. So now Junta testing in the standard model is pretty well studied, and it's known now that it requires k log k queries with adaptivity, and it requires k to the 3/2 queries without adaptivity. Unfortunately, though, the model isn't super satisfying because it's not very robust to noise. So if you take a k-Junta and you add just a little bit of noise, the tester is allowed to reject. But morally, really we'd like to call a function, that has like 99% of its variance explained by some set of k coordinates, a k-Junta. So this motivates the following tolerant Junta testing problem. So here, again, there's an unknown function f, and we want to design an algorithm that accepts if there's a k-Junta that agrees on, that only disagrees on almost epsilon1 fraction of values. So for instance, like this should, just to make it concrete with constants, maybe, we want there to be a k-Junta that agrees on 99% of inputs, and we should reject if it's epsilon too far from any k-Junta. So meaning maybe, for instance, every k-Junta disagrees with it on 10% of its inputs, right? Again, we're going to be interested in the query complexity of sort of distinguishing these two scenarios. Now, this model's been around for a while, and it's now known that it's strictly harder than the standard model. So Levy and Weingarten showed a k-squared lower bound for constant epsilon and epsilon 2 if your tester is non-adaptive. This was later improved by Poilievre et al. And Chen et al. To get a 2 to the root k bound for non-adaptive testers. And finally, Chen and Patel showed a k to the 100 query lower bound for adaptive algorithms. So on the up-bound side, we also have some we know some bounds as well, although they deviate a lot from the lower bounds. So Blay et al. Showed a 2 to the k upper bound for by a non-adaptive algorithm, but it sort of required epsilon1 and epsilon 2 to differ by a constant factor here. Day et al. Then showed that actually you don't, this problem is testable even if the gap is arbitrarily small and you don't have this constant factor. And again, they gave a non-adaptive algorithm and they used roughly exponential and k queries. And most recently, Ayer et al. Showed that actually, if you give yourself adaptivity, you can get a 2 to the root k bound. Great. In this work, we get this 2 to the root k bound even with non-adaptive algorithms, which recall actually matches the lower bounds. And we also improve the epsilon dependence to make it logarithmic in the exponent here. So just to reiterate, we show that there exists a non-adaptive tester that makes 2 to the O tilde of square root k log 1 over epsilon queries. And we actually also prove a lower bound that says that we need 2 to the root k log 1 over epsilon queries. So the place where this sort of deviates from the previous known lower bounds is exactly in including this epsilon dependence here. Great. So how do the lower bounds go? So essentially the lower bounds proceed by making the following gadget. So you need to design distributions over functions from plus minus 1 to the k, such that the distributions are identical on balls of relatively large radius, where here relatively large we're going to take to be root n log 1 over epsilon. And the second property that we need is that the distributions have different expected distances to being constant. So we're going to go ahead and look at these two distributions here. And how do we draw from the first one, ds? We'll flip a coin. If it's heads, we'll take this first function, which think of the blue values as being +1 and the red values as being -1. So this function is +1 on the top half, and the bottom epsilon mass is also +1. And sort of the middle layers of the cube are enabled -1. If we flip tails, though, then we'll just output the all -1 function. Similarly, for d no, if we get heads, we'll output the majority function. If we get tails, we'll output sort of, it'll be +1 on the bottom epsilon layers and -1 on everything above it. Now I need to convince you that we have these two properties. The first one is sort of like a proof by picture. So if we take a point here, let's just say we pick this point, if we drew from ds, half the time this point is, blue on top with red on the bottom. The other half of the time it's all red. And if you look over at d no, it's exactly the same, right? Half the time it's blue on top with red on the bottom. Half the time it's all red. And so this gives us our lower bound here. This gives us, that they're identical on balls of radius. Or, you sort of just check the additional cases in this same exact way, and you can see this. I also claim to have epsilon expected distance to being constant. And this is, something we can just say the difference between their distance to being constant is roughly epsilon. And this we can kind of just check. So, if we look at this first distribution, half the time we have to change nothing, and half the time we have to change 1/2 minus epsilon. So this first distribution has an expected distance of 1/4 minus epsilon over 2 to being constant. If we go over and look at d no now, half the time we have to change half of it, half the time we have to change an epsilon fraction. So that's 1/4 plus epsilon over 2. And so again, you get this different expected distances to being constant. There's this epsilon gap, right? So now how do we actually use these lower bound gadgets to get our lower bounds? So we'll do this by constructing two distributions over functions from +-1 to the 2k to +-1. And what we'll do is we'll sample a set of k coordinates. And essentially, we want our function to look like it's a Junta on these k coordinates, let's say. Now, for each setting of these sort of j coordinates that we say is important, we're going to sample a function g. And now to evaluate the function, we'll sort of look at these j coordinates to tell us which function g to use. And then we'll just plug in the remaining coordinates that we haven't looked at yet into this g function, right? And to get the other, this is how we sort of get the first distribution of our functions. The other distribution of our functions is you do the same thing, but you just use d no here. It turns out that when you do the calculation, the expected distance to being constant here is exactly going to be the distance to a Junta pretty much in this lower bound instance. So because they have this gap here, there's a gap in how close these are to being Juntas, and so the tester needs to distinguish between them. But on the other hand, the property of being identical on all these balls means that they're hard to distinguish. And so any algorithm that distinguishes between them must make many queries. And so this is how you get the lower bound. Great. And so now, how do you get the upper bound? So essentially, the motivating question goes as follows. It says that if you want to prove an upper bound, you really need to be ruling out the existence of these lower bound gadgets. And so how can we do that? One way of doing that would be by asking, can we use these balls of radius, r, which is, think of as like root n 1 over epsilon, to compute the mean of the function? And maybe the question is, how small can we take r, So, just to formalize this a little bit, given a function f, we want to construct an algorithm that, takes as input this point x, queries points in a ball around x of radius r, and outputs some number mu of x, and we want it to be the case that mu of x is close to the mean of the function over the whole cube. And, there can be some errors. Some x's you pick may be bad. We want it to be the case that most x's are good. So like with 99% probability over the randomness of x that's chosen, we succeed in outputting a good estimate. And the first thing that I want to note is actually we need to have balls of radius at least square root n. So why is that? So it turns out that to see that, we can look at the majority function. So, we take -1 on the bottom half of the cube, +1 on the top half of the cube. And, if we sample a random point x, then its distance to the middle is going to be roughly root n, right? So if this ball has sufficiently small radius, it's only going to see -1 valued points. And it turns out if you only see -1 valued points, you really should think that the mean is just -1. Because, you could have just been looking at the constant -1 function, right? And so this point pretty much needs to output -1 as its value. But then that will essentially, the true mean of this function is 0, and so it won't be giving us a good estimate of the mean. So the radii really needs to be at least root n. And sort of our main technical lemma is that actually, balls of this radius also suffice for, computing the mean. And the proof combines Fourier analysis and the flat polynomials of Kahn, Laniel, and Samrudinsky from their approximate exclusion. Great. So I'll end now with some open questions. So first, does adaptivity help with tolerant Junta testing? So we've reached the point where now the adaptive and non-adaptive bounds are the same. And, there's a big gap for the lower bounds for adaptive algorithms. So, does adaptivity help, or can you bring the lower bound up? Another question is, can we distinguish between functions that are close to k-Juntas and those that are far from 2 k-Juntas in a polynomial number of queries? So note that we're sort of relaxing when we need to reject. And you want to know if sort of this makes the problem easier. And things along these lines are known. So I think Ayer et al. Showed that, we can distinguish between k-Juntas and those far from k over epsilon squared Juntas with a polynomial number of queries. And so really the question is, can we get this to be a constant instead of this 1 over epsilon squared? Or, it's this gap squared. Another question is, our tester runs in exponential time, even though it's like very query efficient. Can we actually get something that's polynomial in the number of queries? And finally, more generally, we're interested in understanding whether these local mean estimation tools are useful in other places. So for instance, we can get some results that, as far as I know, are new, at least to me, of, for instance, an AC0 circuit. It turns out that if you have a low depth AC0 circuit, a ball of polylogarithmic radius suffices to actually learn the function under the uniform distribution. So things like this, so it does seem like there's maybe some more juice to be extracted from these local mean estimation tools. Anyways, that's all I have. Thanks for listening.